Hello and welcome to Learn Synthesis with Pure Data, Series 1, Episode 2. We're going to learn about overtones, undertones, harmonics, and partials. This is essential stuff in learning about tone color, which is at the heart of synthesis. I'm Dr. Lawrence W. Moore, and we're about to learn something that is at the core of synthesis. We're going to learn how tone color works. And in order to explain this concept, basically, if you were to imagine a clarinet and a flute, and both of them are playing the exact same note, the clarinet still sounds like a clarinet and the flute still sounds like a flute. Why is this? Well, basically, within the frequency material that both of those instruments are playing, there is basically something we call tone color. Basically, the amount of frequency content and the characteristics of it for each instrument makes it sound like what that instrument sounds like. In the natural production of sound, this is achieved through, the design of the instrument, the way it makes its sound vibrations, and also the shape of the instrument and other factors go into making it sound like what it sounds like. In synthesis, we get to create what things sound like, but we still need to understand how tone color works in order to make the sounds that we make. And that's what we're going to be doing in this episode. So let's get to it. And before we get to pure data, we're actually going to use Adobe Audition here. Those of you who are following along, you do not need to do this in Adobe Audition. This is not something that's part of our creative process. So this is just information for your understanding. Okay? So what I'm going to do now is record something. I'm going to make some sounds with my mouth, record them, and explain some concepts to you. Okay, so here's the record button. Let me get ready. I'm going to sing some things that are going to sound maybe a little bit strange at first, but they're going to be useful in explaining these concepts. Oh, wow, that's just what I needed. Let me see something here. Got to make sure that that we have the right stuff set. I'm going into the settings here of Audition and make sure that we have the right audio hardware. That's what I want. Let's see what we got here. Yeah, I don't have the right input set. I'm using a Motu interface here. And gonna make sure, here it is, right at the top, but it wasn't the one selected. There we go. In 1, 2, out 1, 2. We're good to go. If anyone wanted to know how to set up your audio hardware in Adobe Audition, that's how you do it. Okay, what I did there is I basically sang, maybe the tuning's not perfect, but basically the same note in all three of these different sounds that I made. same musical note, but I changed my mouth and nasal cavity a little bit in order that I made three different types of sound on the same note. And what we're going to do now is look at what's different between these sounds. And we're going to do so by using what's called the Parametric Equalizer in Adobe Audition. And right here it is. And basically, this display is going to be helpful to us because it's going to show us from down at 20 hertz, the ideal lowest frequency that the human ear can hear, up to 20,000 hertz, the highest frequency ideally that we can hear. Usually we don't necessarily hear all the way down to 20 or all the way up to 20,000, especially all the way up to 20,000. By this time of my life, my hearing is probably down to somewhere around here. We'll see. But in any case, it will display the frequency material throughout the frequency spectrum so that I can see visually what goes into making up the frequency content of this sound. When you produce sound naturally, it's just a part of nature and so forth that other than the frequency of the note that you're singing, you will also have other frequencies in the sound. And this is the same thing for any kind of acoustic instrument or any natural sound production. There is always other frequencies in the sound. When you sing as opposed to talking, you're focusing your vocal cords such that you'll make one frequency stand out the strongest. And that will be basically considered the note that you're singing. You could sing a note that's the same on a piano key that you press, or a note that you play on another instrument, and thus you'll be hearing and singing the same note. And that is the frequency that stands out the strongest. We call that the fundamental, incidentally. So now from now on, when I'm referring to it, I'll say the fundamental. The fundamental pitch of the sound, the one that you hear as the musical note that is being produced by any pitch-based instrument, which means any instrument that is capable of playing sounds with a fundamental pitch that stands out the strongest. Now, I'm not sure why I'm hearing that other beeping sound. It may be a conflict between my screen recording software and using the same device here in Audition. Strange, but whatever. Try to ignore that. That is not, part of the sound what I was singing, and it's not part of our discussion here. But anyway, let's just hear this again and see it. And what you're going to look for are spikes that stand up strong. You'll see one spike somewhere in this area that stands up the tallest. That means it's the loudest or has the most intensity behind it. That'll be the fundamental. And then you'll see some other spikes stand up as well. All right, that's the second sound I made. I forgot to rewind. But you did see those spikes I was talking about. But since that happened, I might as well say we're going to see between these first two sounds that I sang. The first one, you'll see a spike stand up strong as a fundamental, and the second one, you'll see the same. But the second one, you should also see some other spikes here that are taller than the ones that you see in the first one. So here we go. Okay, tall spike here, here's the fundamental. And then there's some spikes here separated by some space horizontally. These are called harmonics. those are frequencies in the sound that you're producing that help make up what's called the tone color. The tone color of a sound is its unique sound, just like I say, what makes a clarinet sound like a clarinet, what makes a flute sound like a flute. And what's unique characteristics of harmonics is whatever the frequency of the fundamental is, they are whole numbers times that frequency. The fundamental is considered to be technically a harmonic in and of itself that is 1 times the frequency. And 1 times whatever frequency in hertz that this note is going to be itself. 1 times anything is itself. So that is still considered to be a harmonic. It's harmonic number 1, 1 times the frequency. And then the next harmonic up would be 2 times the frequency. So whatever frequency I'm singing, and I'm going to zoom in to see here, at least roughly, looks like somewhere between 200 and 300. Let's say somewhere around 250. So if this is 250, 1 times 250 is 250. That's the fundamental, harmonic number 1. Harmonic number 2. Now, in natural sounds, these harmonics may be stronger or weaker, depending on how the sound is produced, and that's kind of like making up the unique fingerprint of that sound, its unique tone color. So let's say this is 2 times 250, and it seems to be roughly in that area. So it's not exact, but let's just say it's 500 hertz, 2 times that frequency. Then 3 times that frequency would be the next harmonic up. That would be about 750. And then 4 times that frequency would be the next harmonic up. 4 times 250 is 1000, and this is roughly there. So yeah, this would be harmonic 1, harmonic 2, harmonic 3, harmonic 4. And harmonic 1 is the fundamental pitch. The note that we hear as the musical note being sung. Now, we're about to get to the next sound I made, which will still have roughly the same fundamental. Since I didn't hold the pitch exactly stable with my vocal cords, it may fluctuate left to right a little bit. Okay, now what you're seeing is some more spikes appearing up here. Because I went E or E, what I was doing was I was kind of like squeezing my sinus cavity a bit, which helped to produce some higher frequency content in the sound, a different tone color, what we would call a brighter tone color. And the result is it basically has higher frequencies within the sound. So there's more strength in the upper harmonics of the sound. And thus we hear a different tone color, and the result of which is you have some other harmonics that are coming up. 5 times the fundamental, 6 times the fundamental, 7 times the fundamental. The harmonics tend to be the spikes that stand up more so than the kind of like solid mass down here. And those would be harmonics as well. Harmonics are whole numbers times the fundamental. Now let's hear the third sound that I made. What I'm expecting to see here, and hopefully it'll be that case, is that some of this space in between the harmonics, especially up in this area, is going to be a little bit more solid. You'll see a little less distinct spikes and more of just a rising up of frequencies in this area in general, like across the board. All right, here it comes. Yep, and that's what we see. You notice how we don't see those harmonics sticking out as much. We see a lot of the material in between rise up. And so the harmonics are not sticking out as strong in this area kind of like in the area where I was making the buzzing sound, this kind of, yeah, buzzing sound with my mouth. And so we still see the strong fundamental. We still see a couple harmonics here, 2, 3, and 4 sticking out. And then here we see more of a mass. The harmonics are not sticking out above the in-between material as much. Now this in-between material is what's called partials, because these frequencies are not whole numbers times the fundamental. These would be frequencies like that between 5, 6, 7, and 8. So they would be frequency numbers, if you were to analyze them, that have decimal points after them and numbers in between. Those are called partials. Both harmonics and partials are what we call overtones, frequencies above the fundamentals. And in natural sounds that get produced due to their acoustic nature, like if it's an acoustic guitar, for example, there's a box in which the sound resonates. And when you have sound resonating in boxes of different types, materials, and shapes, you do get, from the resonating chambers of instruments, what are called undertones. Those are frequencies lower than the fundamental. They tend to be quieter overall, but they are lower frequencies from the frequency material or the sound vibrations within the acoustic chamber of the instrument that get bounced around and kind of, slow down the vibrational speed of some of the sound vibrations and thus create some vibrations here that are slower or lower. And so you have some lower frequency material than the note you're singing that are a part of the color of the sound. So overall, we have undertones, we have overtones, but in the overtones, we have two distinct types. The harmonics that are whole numbers times the fundamental that tend to add more of a harmonious sound to the fundamental, and we'll see why in a little bit. And then we have the partials that, as far as tone color is concerned, tend to add a rougher or less harmonious or non-harmonic sound to the tone color. But either way, the whole concept of tone color is, in these three different sounds, I'm singing roughly the same note, and they sound different because of the frequency material in them, in how I produced that note that I was singing. So now let's take a look at some other software here that I have to take a look at this frequency content in another way. So I'm going to close Audition. And actually, it's good this web page is appearing here, because this is a web page for the software I'm about to use. It's called Spear. It is a free download. If you go to its downloads page up here, you'll be able to download it for Mac, Windows, or Linux. And basically, what Spear is, it's a software produced by a gentleman named Michael Klingbeil, and it is a software that has a display like this, where it displays the components of the sound, the frequency material of the sound. In this case, we look at the frequency measurement using the left axis, the vertical axis, in which case frequency is being analyzed from low up to high. Now, I actually have the software here, and we're going to load in, just a moment, the sound that I just produced. This is a file that Adobe Audition makes that we don't really need. It's for the graphic display of its waveform. But here's the sound I made. I recorded it into this week's folder, and it's called Voice, simply. Now we're going to load that into Spear, which I do have open right here. So I'm going to go to File, Open. Now we're in Documents, PD. right here. Learn synthesis with pure data, series 1, episode 2. And here we go. Let's double click this. Now here it's asking about the way in which you want to analyze this sound. I don't need to change any of this material. It's a mono file, so only one channel will come in. And I don't need to change any of these details in order to do what we're doing here. So I'm going to click Analyze, and it's going to load in the audio and give us an analysis. Now, what this is this is displaying. It's not a display like what we saw before. The horizontal axis is time going forward. The vertical axis is the frequency content of the material. And it's kind of zoomed in right now. It's only displaying this frequency range right here that we see to the left, you know, up to about, let's see, I got to zoom in to see the number better, pardon me. 15,000. Hold on, or is that 1,500? 1500, yeah, 1,500, I was going to say. So that is, you can have it go up to 20,000 by zooming in. Over here, there's a plus and minus. This will allow us to zoom, well, actually zoom out to display more of the frequency spectrum. But with the harmonics that we're going to be looking at, I'm not going to need to do that. I don't think. We'll see as time goes on. But you kind of see the spaghetti-like material here. Now, since this sound had some beeps and other noisy stuff in it, that's probably going to get displayed as well. And I'm kind of guessing it's some of this stuff here. But with this displays, and typically even when you think it's silent, you know, in your room, there are other sounds in there, very quiet. And those would appear here in the analysis as well as light, very light gray material. But this includes your harmonics and partials, your overtones and undertones. Here, this dark line, this is where I sang the note, and here's the fundamental pitch of the note. And the harmonics above it, I believe, are here, here. They tend to be the straight and more stable lines because they're kind of, as I'm holding the fundamental pitch, they are pitches that are holding out as well. But since they're not as dark as the fundamental, it's showing that they are weaker in comparison, which is normal in any pitch sound where there's a specific pitch coming out the strongest, which is any kind of note playing instrument. Your harmonics are going to be quieter. The thing is, they're going to be, in this case, they're significantly quieter, because what I sang was close to like a sine tone type of sound. Not exactly. Can't produce them naturally. You have to synthetically produce them. Sine tones are pure tones that are just one frequency and nothing else. This is not that, but the harmonics are quieter in comparison. So it's kind of close to a sine tone in that the fundamentals really strong and the harmonics are weaker. And there's also not much in the case of partial content, because you see there's even some space in here. There's not much frequency material in between the harmonics. So let's hear it as we see it. Now here the harmonics are getting stronger. That's because this is where I was compressing my sinus cavity, and I was making, as a result, some more higher frequency material stand out. So here you see at least harmonic 2 and 3 are stronger and standing out. Now over here we should see more partials. We're starting from the beginning. Okay, yeah, stronger harmonic strength here, but also you see a lot of this gray stuff in between, the gray spaghetti-like stuff here. Those are partials standing out more. Now I am going to zoom out so we can see more of the frequency spectrum. So we'll see the lower harmonics here, harmonics 1, 2, 3, the fundamental being 1, getting closer together in height because we're zooming out, seeing more high frequency material. You look at this mass of stuff here. That is more partial material. And you see here the harmonics of these partials are not standing out very strong. Now I'm looking up here, over here, to get this selector. This allows me to select in this way. What I wanted to do here, ignore the red outline here. Because I selected, use the selector to move over to the left. I selected a little bit of area and it highlighted it red to say this is what's selected. But look at this middle tone that I sang, since it wasn't as rough and as buzzy as the third tone that I sang, you see some of these harmonics are sticking out stronger. Over here, they kind of blend in with the partials more. Not as much harmonic material. We see more non-harmonic material. The partials are stronger in relationship to the harmonics, especially these upper ones. Because the way I made that sound, the higher frequency material was emphasized and less defined because it's like a buzzy sound. And so we got more of the non-harmonious or non-harmonic overtones making up the sound. And they tend to be the less consonant or less compatible with the fundamental type frequencies, which sound to our ears more like noisy or more dissonant with the fundamental. Harmonics tend to be more harmonious with the fundamental. Partials tend to be more dissonant with the fundamental, making up the rougher tone colors. Okay, so that's a great way to visualize things, and Spear has a lot of other features to it for editing the material. And kind of taking your different partials and harmonics and playing with them. It's a fun software to work with, but it's not part of this lesson, so we're going to close it. And no, we're not going to save the analysis. And there we go. What we're going to do now is go into pure data. So those of you following along, this is where you're going to build with me. And we are going to do something that is related to additive synthesis. We're going to have a more thorough lesson on additive synthesis coming up. I think it's not the next lesson, but one after. But we're going to see a little bit of additive synthesis, which is a form of synthesis where you add together different sine waves. Well, we're going to first of all make our first sine wave. Since last week we were recording sound, we didn't actually make a sine wave. We're going to make our first oscillator and our first sine wave today. And then we'll make some more sine waves to kind of explain the harmonics concept further. Let me do this. Get this a little bit bigger here. Okay. And I'm going to hit Control plus, Command plus, and Mac to zoom in because I know what I'm going to make would appear a little too small. First, I'm going to make an object. Control 1, Command 1, and Mac. Shortcut for making an object. And the object I'm going to make is OSC tilde. Then I'm going to put a space. And now I'm going to put a number, 440. Click outside the box. It takes, it's a valid object. The OSC tilde object simply stands for oscillator. And what it makes is a sinusoidal wave shape. We'll be seeing that in a moment to explain exactly what that is, but you can consider it to be a pure tone, a single frequency without any harmonics or partials in it. These types of sounds can only be synthesized either with electric hardware like analog synthesizers or computers, digital ways of synthesizing sound. Now, remember last week I talked about how OSC tilde is an atom, the first atom of an object. It tells it what it is. Put a space, and then the second atom, the second piece of information in the object, is called a creation argument. It's basically something that tells information to oscillator about it. And depending on what the object is, in this case, OSC tilde, it'll vary as to what your creation arguments are and what they tell the object. The first creation argument for the OSC tilde object is its frequency. This is the frequency at which that sinusoidal wave shape will oscillate. So what we're going to do now is, we don't really need to do this, but it's going to be a part of our explanation later, but we're going to make another object. It's simply an asterisk and a tilde. The asterisk in PD is basically a multiplier. It means multiplication. Whatever comes into the left inlet gets multiplied by whatever your creation argument is, if you make one, or whatever comes in the right inlet. When it has the tilde behind it, remember it's an audio object and it allows audio to flow through it. So basically all the different samples being produced by oscillator here, producing all these samples to make up a waveform shape. Those samples are numbers, but they stream at the audio rate, the sampling rate, 44,100 in this case. It multiplies that by whatever you're multiplying it by. Now, I didn't put anything. I'm going to put a 1, which means it's being multiplied by 1, so all those numbers remain the same. It would be the same as if I didn't have this object at all. But since we're going to make some more oscillators and multiply them by some things, I'm just putting this multiplication by 1 here as a visual thing, just as a comparison with the other oscillators that we're making. And then I can make the sound come out so that we can hear it by making a DAC, which we made last time. Control 1 to make an object, Command 1 a Mac, DAC tilde, digital to analog converter. If we want the sound to go out to both sides, we can do that. Now, before this will sound, do you remember the other thing we have to do? That's to turn on DSP. But what I'm going to do is, instead of just switching it on here, we're using the shortcut Control / Command / and Mac to turn it on. I'm going to get us into the habit of making our own messages to turn DSP on or off. So I'm going to do Control 2 to make a message box. We did do this last time. And you put a semicolon, hit enter, and then as soon as you start typing, it goes to the next line. PD, DSP, space 1, and then a semicolon. And this is the message that tells Pure Data to turn on DSP. So audio's flowing, you'll be able to hear the sound and everything. And just for the next time this opens, just so the DSP is on automatically, I'm going to make an object called a load bang, which we did last time as well. And that basically will bang as soon as this patch opens. And that will tell DSP to be on. Now, just so we can easily click something to turn it off, I'm going to copy this. I selected it and hit Control D to duplicate. Command D and Mac, and put a 0 here instead of the 1, which is the signal to PD to turn DSP off. Now I need to go into run mode. That's Control E. Basically, oscillator, when DSP is running, will be running itself. And so it'll already be oscillating at 440 hertz. It'll make a sine tone sound that we'll hear as soon as I turn DSP on. Woo, that was loud. Yeah. Turn down your headphones for now. That's because we could control that and make it quieter by multiplying it by a lower number here, like 0.5, to cut it in half. But I don't want to do that because I need the amplification numbers here to basically explain the concept I'm explaining. So you may just want to turn your volume down a little bit if that was too loud for you. But in order to explain this concept and not have to hear a tone that often, I'm going to make a visual display for the sound that we are producing. So what I'm going to do now is make one of those arrays that we made last time. Control-Shift-A, Command-Shift-A in Mac, or you can go to the Put menu that we saw last time. If you haven't seen the first episode, please go back and see it. This is a series where the learning is in order. And so I'm going to make an array and call it output. It'll allow us to visualize the output that's coming out. And the default size of 100 I'm going to keep because actually it'll work out just fine for us for what we want to see. There we go. Now I need an object that's going to tell this array what's going in it. And what we're going to do this time is use an object called tab right tilde. And then I'm going to put the array name, that's the second atom. This is a creation argument that tells tab right what array to write to, or what table to write to. Remember, the terms table and array for our purposes are basically meaning the same thing. You could think of this as a table and an array. Okay, now, if I do this, the sound that we produce here is going to go into this table right here. So yeah, make sure your headphones are lowered in a safe way, because I need to turn on DSP for this to work. Tab right is an audio rate object. It receives sound in and it will write it to the table. Or not, as the case may be. Oh, I know. Tab right also needs you to send it a signal called a bang in order to write to the table. So, just like last time, I'm going to make a message, type bang. And basically a bang tells tab right to actually do it. So whatever sound is coming in, it'll fill up the table with that sound. This is only 100 in size, so there's only space for 100 samples, so we'll see a little fragment of a waveform appear in here. Here we go again. Actually, just so we don't have to hear this tone, I can get rid of it by disconnecting the DAC, so we don't have to hear it. Besides, we want to see it right now. All right, sound's running. We don't hear it because I disconnected the DAC. Gonna hit bang. There we go. It took a snapshot, and the reason why, I'm going to turn off DSP now. The reason why we see this is we're seeing a sinusoidal wave shape that has populated the table. This is about how much 100 samples can display. So whatever shape the waveform is that's coming into tab right, it's going to display as much of that as the table size allows. And so we see, and this is why I stuck with 100, because at 440 hertz, you could easily see like just about, you know, a nice clean cycle of the waveform It's not exactly one cycle, but you know, it's good for our purposes in visualizing the sound. See the smooth round shape of the sinusoidal wave shape coming in, which you could think of as a sine wave. And the oscillator object basically does emit sine waves. Technically, it emits them, but in a different phase of the waveform. It's for all you out there that know better, but don't worry. That's not important to us because for all intents and purposes, for us, it's the same. So here we see like a sine wave, just about one cycle of it. Okay, which means one crest to one trough. The crest, it's starting in the middle of the trough, going up to the crest and down to the trough again. And so that's why it's in the shape that it's at. If we hit that bang different times, we'll see it in different positions or different phases of the cycle of the wave. Now, if we don't want to just sit here and keep clicking bang, we could actually have this kind of like show an animated wave shape. What we need to do is bang this multiple times automatically. And we could do that with an object called Metro. I'm going to move this stuff up here so there's some space, so things look nice and neat. Object, Control-1, Command-1 in Mac, Metro, no tilde, put a space, and now the first creation argument of Metro, I'm going to put in 100. Now let me explain this. Metro is an object that sends out bangs, like a metronome would send out clicks. Basically, it sends a bang out of here, which will bang the message object, which just continues the bang along into tab right. So tab right gets its bangs, but it'll get it periodically based on the creation argument you give it. You could change the value here by sending information in through its right inlet. But basically 100 here means 100 milliseconds. So you put in a time in milliseconds that tells it how long to wait before sending the next bang. 100 milliseconds is 1/10 of a second. So that's fairly quick to us. It's hard to count to 1 through 10 in 1 second. So it's a pretty fast interval of time. And then what we need to start the Metro is, believe it or not, another bang. That'll tell it to start. Sometimes it can be confusing because last week we used a write SF object, and to start it, the message actually had to be start. Oh, this is good that I did this. I accidentally made an object, and you see I typed bang into it. This isn't going to work. Bang needs to be sent as a message. The object accepted bang as a valid object, but for us to be able to click on it and send the bang, we want it to be a message that has that indentation to the right. Control-2, Command-2 in Mac to make a message as opposed to an object. But I know that a lot of times when people are starting off in PD, they'll accidentally make an object and type something that's intended to be in a message box in the object. So it's good I did that, because that will probably happen to you at some point. Just by accident, you make an object, type message information in, and it won't work right. So anyway, that starts Metro, and if we ever want to stop it, it does accept a stop message. This is why also you will need to sometimes check the help file associated with your objects by right-clicking and going to help, because it tells you what information it will receive and stuff like that. And here, well, let me zoom in on this. See, it also accepts 1s and 0s for starting and stopping. 1 or a bang, 0 or a stop message. So you got to check on that stuff. Sometimes a bang starts things, sometimes it's the start message. So I'm going into run mode now. Control-E, Command-E in Mac. So I can click our bang. Oh, DSP is not on, so it's not flowing. There, I turned it on, and you can see Metro is operating. And so we see an animated waveform display of what's coming out of OSC tilde. And so this would be considered a pure tone. Its smooth round shape is because it doesn't have any harmonics or partials in it. Now what we're going to do is see how, and I'm actually going to give myself a little more vertical space here so things look nice and neat. I'm back in edit mode. I hit Control E so I can move things around. Put this down a bit. Yeah, let's put this over here. Now what I'm going to do is make some more oscillators. We're going to add more pure tones to this. And we're going to do them at the frequencies of harmonics. And we'll keep this DAC here because we're eventually going to use it, but I think I'll put it on the other side, right about here. And move this over. Okay, so I'm going to select this, drag select, hit Control D, Command D and Mac. Take the blue highlighted thing. Incidentally, when you duplicate like that and it puts the duplicate material on top of the other material, you'll see that the thing that's new is kind of like highlighted in blue. And you want to click on it, any part of that selected area that's blue, and drag. If you don't do that right, like if you click and space to the side, it'll leave this on top of this and it'll look cluttered and stuff. And you don't want that. So while it's blue, just be careful and drag by selecting the blue objects. Now, we're going to need our first harmonic overtone, which is the second harmonic, 2 times the fundamental. So we could just type that in here and just say 880. 2 times 440 is 880. It's an octave higher for those playing the home game. And what I'm going to do here, incidentally, this extra bang here in between Metro and tab right is not necessary. I'm going to delete it now. Select and hit delete or backspace and connect Metro up that, because Metro actually emits bangs, so you don't need to have it bang a bang message. It's like a duplicate bang that's not necessary. I'm actually going to move, we'll see as we make things where I need to move it so things don't get cluttered. But what I'm going to do now, I'm going to disconnect this cable and you'll see the table stop because there's no longer audio going into it. And what I'm going to do is add these two together. Now, if I do it like this with both of them being 1, let's see what happens. Control 1 to make an object. I'm going to make an adder object, a plus and a tilde. But what this does is it adds whatever's coming into the left inlet to whatever comes into the right inlet, which is how we'll use it. Or you could put a number here to add numbers to those numbers of the samples coming through. But in this case, we want to add together these two signals. Now look at that. It's stretching down below the box. What that is the two waveforms being added together, which means now since it's going above 1, which means it'll also go above -1 or below -1. That's exactly what's happening here. It's going to go outside the box because they're being added together. To deal with this, since as we add more oscillators, we're going to want to make sure things stay in the box. If we were to listen to this, it would sound distorted, even more distorted than things already sound. We're going to attenuate it, reduce it. We're going to make a multiplier object that cuts it in half. And so you can see here, remember it's a star tilde because sound is going through it. You can see here, digital audio is numbers and math. So there's the shape of our waveform. Now, what I need to do, we're still not doing harmonics because really, since these are both at 1, they're equal strength. It's basically 2 tones at once. So they would sound like a harmony, a note and the octave above it. But we're going to get to doing it as a harmonic in a moment. There's a lot that can be learned from this as I'm going through this process. That's why I'm going through it this way. Let's give ourselves a little more space. Yeah, keep these up here next to the objects themselves. Okay. Now, one other thing that's giving us this shape is you can see there's a faster frequency along with the slower frequency. The big crests and troughs are the 440, and there's an 880 in there that's kind of trying to cut it in half. But the way in which we can make this more accurate is to make sure these waveforms are starting and ending at the same location, meaning in phase with each other. And in order to do that, there is a phase message that can be sent to the right inlet of an oscillator. Now, phase is measured as 0 to 360 degrees. But in PD, that's expressed in a range of 0 to 1. So I'm going to make a message, Control 2, Command 2 on Mac, and just put 0. 0 means the phase it begins with. In other words, start this sinusoidal wave shape right at the beginning of its shape. And what this essentially does, it doesn't matter if I put a 0 or 1 here for our purposes, but we want to send phase to these two objects at roughly the same time, which is what we're going to do here by clicking this one message. It'll send a phase number to both of these, so it'll make them in phase with each other so they'll line up. There we go. So this is the wave shape we get when that happens. Now this is the shape of 440 and 880 at equal strength. What we're going to do next, and actually if we were to hear this, let's temporarily hear it a little bit. I'm going to have to take the sound out of here. Since it's being multiplied by 0.5, it might be quieter, but just be careful with the volume anyway. Okay, remember how now this is 2 frequencies at equal strength, so it's kind of like the lower note and the higher note at the same time. What we're going to do is now make this a strength that's more like what a harmonic would be. They're weaker than the fundamental. That's why you hear the fundamental as the notes you played, and the harmonics just add color to the sound. Probably about the loudest you'd want a harmonic to be would be 0.5. For those of you who know this already, I'm basically doing the formula for a sawtooth wave shape. There we go. We quieted that other harmonic a little bit. So let's hear it now. And you know what I'm going to do? I'm going to multiply it by 0.2. Make this quieter so we don't have to worry about the sound being too loud each time it comes out. So let's hook it up now. To the DAC. There, that's more manageable. I'm going to turn DSP off and we see it frozen in time there. And I'm going to connect it to both sides because from now on we're going to hear it while visualizing it. Now that I have it at a nice level that doesn't hurt. Thinking. Yeah, let's put it over here so the DAC's out of the way and we don't have its cables covering other stuff up. There we go. All right, so now we're hearing as our fundamental A440. That's the note we're hearing. But now this harmonic is adding color to the sound. So with that higher frequency material in there, the sound is sounding a bit more colorful. It's having more higher frequency material in it. Now let's do this. We're going to make 2 more harmonics now. I selected those 2, Control D, grab them while they're blue, move them over here. The next harmonic would be 3 times the fundamental, that's 1,320. The 4th harmonic, or 3rd harmonic overtone, would be 4 times the fundamental, that's 1,760. And what we're also going to do is typically harmonics get quieter as we go up. And since I'm doing the sawtooth wave shape, I'm going to use that formula where I'm going to use a strength. And this we're going to go over in more detail. We're going to actually make the 4 basic wave shapes next week. And then we're going to make them using just sine waves in the following week. So you'll see how that works. And we'll see this formula again. So that's being multiplied by 0.333, quieter, and then this will be even quieter, 0.25. Now we need to add all 4 of these together. And the way we're going to do that, I'm going to disconnect this one here. To disconnect cables, just hover over them in edit mode. They'll highlight. And you'll see an X, and you just click on them and press delete. Well, you highlight them by clicking on them with the X and then hit delete. We're going to need an adder here, plus tilde. We're going to add together these 2. Oops. And then we're going to need another adder, plus tilde. We're going to take the output of these 2 and add them to this. So we're basically daisy chaining adders here to combine all these signals together. Take this here, add it to that. There we go. Now also we're going to make these line up in phase. Right inlet. Now these won't line up in phase until I click this message to send it. So let's turn it on. You hear about how by adding these upper harmonics, we are adding more higher frequency material to it. So it's starting to sound a little bit more nasally and brighter because there's more high frequency material to it. And its shape is starting to take on more of one big slope and going down. It's starting to get closer to the sawtooth wave shape that I spoke about before, which we'll be learning about in 2 weeks. Well, actually, we'll be making a sawtooth next week along with the other basic wave shapes. But in the week after is when we're going to make them using sine tones in truly doing additive synthesis. This is already additive synthesis, but there's an easier way. I'm just doing it this way to explain concepts. Now, you hear how it still sounds kind of like a solid tone. It's just a brighter tone, more nasally tone than the sine tone. But harmonics, as I said before, are harmonious overtones that basically help support the fundamental and interlock with it. And the reason being is, if you were to imagine here, one cycle of a wave shape that's A440, the 880 hertz version would have two cycles in the same amount of space. But at the end of those two cycles, they would line up together. And then the next harmonic, 3 and 4, would have three cycles in that space, 4 cycles in that space, and at the end they would line up in the completion of their cycles. In other words, they kind of interlock with one another, which to our ears sounds like basically like a compatibility that we would call harmoniousness or consonance. So the harmonics tend to add consonant upper frequencies to the sound. Now let's do something a little bit different here. Let's take, instead of having this fourth harmonic here, we're going to make this into two different things. That instead of being a whole number times the frequency, we're going to make these not whole numbers times the frequency. So in other words, I need to shift it off, and we could do that by just shifting it off as 1760. And I'm going to do them by equal amounts just for the hell of it. They don't have to be, but let's say, for example, I make this 1755 and make this, conversely, 1765. Now what I have are two partials here. They're overtones, but they're partials now. And they're both going to be equal strength here. We'll see how that goes. They're both 0.25. Actually, let me make them a little bit quieter just so we don't get too loud. Let's make it 0.15 and 0.15. I'm not trying to use these sine waves to make any specific shape, but I want you to hear the difference between the partials and the harmonics. Now that we're, instead of having a whole number times the fundamental as a harmonic in the sound, we are going to have partials. I had to make another adder, connect them up, and then connect it up here so that we hear everything combined together. So this should sound a little bit different, a little bit more dissonant. Now typically, a more dissonant sound would have a bunch of partials in it. But just by having these here, the sound is going to sound a little bit more tense than before. And by them being off by the same amount, we hear a pulsing effect. We've actually created the effect of beating in the sound. By being 5 below and 5 above, we're hearing that kind of pulsing sound in the sound, which is kind of like the like when you have two notes that are out of tune with one another but close, you can hear this sound of beating. That's the pulsing that you hear, because it's off from what it should be and to be in tune. And so you hear the two in tune and out tune notes kind of like challenging each other, so to speak. There we go. So that's adding roughness to the sound. Now let me make it let me think here. How about we just add another partial? Just one. And hear it get even a little bit more tense. So we're going to add this to our new partial with this other adder that I made. And take the sum of those, put them in there. Select this. 125. Let's make these all quieter. Actually, I'll keep that at 0.15 and stuff so that we don't hear as clear of a pulsing effect. But as I'm adding this partial here, we got to give it a frequency. Let's say 3262. All right. And now, you hear that higher pitched part of the sound up there, but basically it's sounding more tense. And to make these harmonics blend a bit more, I'm going to make them all quieter. Let's say 0.2 and 0.2 here. Because these are much stronger than these. Let's make them blend a bit more. And all the time, we're changing the tone of the sound. Now, by these two being separated by a small amount, we're still hearing that beating effect. We could get rid of it by taking this frequency and just not having it as close to this one. So let's do like 2001. Why not? I'm not worried about putting these all in phase or anything right now, because now we're talking about the tone of it. The phase was just mostly for visually seeing what the shape would look like. Although, when they're all in phase with one another. Although, why not? Let's just look them up. It's there already, so just do it. There we go. Phase won't really change the sound too much in this circumstance. So you hear that? There we go. So anyway, I'm going to save this. So anyway, what you can see from this episode is by putting in these overtones, both harmonics and partials, we can change the tone of the sound. As long as you have a strong enough fundamental, it'll still sound as whatever note the fundamental is, but it will be a different tonal quality to the sound, a different tone color. Save it again. There we go. I'm going to take a screenshot of this. Yeah, that's good. Let's take a screenshot for the thumbnail. So anyway, I hope you found this somewhat valuable. I mean, you could play around with all sorts of sine tones, going higher and higher in frequency, making harmonics and partials and seeing what kind of wave sounds you get. One thing that still will make this sound less interesting is it's periodic in the fact that it's the same shape over and over. Each cycle, it's the same wave shape. It doesn't change over time, so it sounds very static. But this is like for building the building blocks to sounds. And this is seeing how basically it works. Now what we're going to do is next week learn the 4 basic wave shapes and make them. And we'll actually use that for our eventual building of a synthesizer, because we want to move along. We want to learn these fundamentals, but move along and make things. So we'll also make it into a multi-oscillator where you can select what wave shape you want on the fly from those 4 basic wave shapes. Okay, well, thank you for joining me. If you found this information useful, please do hit the like button. It helps the series out immensely. And if you want more content like this, please subscribe to the channel and select notifications if you want to be notified when a new episode comes out. Yeah, I took the screenshot. Good. All right, well, thank you for joining me. And until next time, do take care and happy synthesizing.